You know, from the coffee that gets you going in the morning to the very air you're breathing right now, solutions are absolutely everywhere. We're surrounded by them. But have you ever stopped to think about the invisible rules that govern how things mix? Or sometimes why they refuse to? Well, that's what we're diving into today, the hidden chemistry of solutions. So, let's start with a little riddle. What could the air we breathe and a can of soda possibly have in common? It sounds a bit strange, right? But the answer is simple. They're both solutions. And that one little fact just blows the doors wide open to a whole world of chemistry that goes way beyond just stirring some salt into a glass of water. Yeah, when most of us hear solution, our brain immediately jumps to a solid, like sugar dissolving in a liquid, like water. But honestly, that's just the tip of the iceberg. It's just one tiny piece of a much bigger and way more fascinating puzzle. And look at this. What a puzzle it is. This table shows us there are actually 9 different kinds of solutions. Of course, you've got your standard solid and liquid, but you can also have a solid dissolved in another solid. That's what metal alloys like brass are. Or get this, a gas dissolved in another gas. That's literally what air is. All of a sudden, the whole idea of a solution gets a whole lot bigger, doesn't it? Okay, so to make sense of how all these different mixtures work, chemists like to start with a simplified model, kind of like a perfect world scenario. They call it an ideal solution. And this perfect behavior is described by 2 really fundamental laws. First up is Henry's law. The best way to think about this is a can of soda. To get all that bubbly CO2 to dissolve in the liquid, the factory cranks the pressure way up inside that sealed can. Then, what happens when you pop the top? Psst! You release all that pressure. Suddenly, the gas isn't as soluble anymore, and it rushes to escape as bubbles. That fizz? That's Henry's law, right there in your hand. The second big rule is Rolle's law. Now, this one sounds a little more technical, but stick with me, it's not so bad. It's all about how easily a liquid escapes into the air as vapor. Basically, Rolle's law predicts that if a solution is, say, 70% liquid A and 30% liquid B, the vapor floating above it will have that same predictable ratio. And it's this perfectly predictable behavior that really defines what an ideal solution is. So, in this perfect textbook world, an ideal solution is just perfectly behaved. When you mix the parts together, there's no change in heat, no change in volume. It's seamless. The molecules don't really care who their neighbors are. The attraction between all the different particles is basically the same. And, of course, they follow Raoult's law to the letter, every single time. But as you've probably guessed, the real world is almost never that perfect. Most of the solutions we encounter are non-ideal. They break the rules. But you know what? The ways they break the rules are actually what make them so interesting. And it all comes down to one simple thing: how much the molecules like each other. If the different molecules in the mix aren't that attracted to each other, they can escape easily, which creates a higher vapor pressure than predicted. We call that a positive deviation. But on the flip side, if they're really attracted to each other, they cling together tightly in the solution, making it harder for them to escape. That creates a lower vapor pressure, and we call that a negative deviation. Okay, this next part leads us to one of the coolest and most powerful ideas in all of solution chemistry. It turns out some properties don't give a hoot about what you dissolve. They only care about how much stuff you've dissolved. I mean, just let that sink in for a second. It's a pretty wild idea. For some very important properties of a solution, it just doesn't matter if you're adding salts or sugar or some other random chemical. All that matters is the total number of individual particles you've added to the mix. And these very special properties have a name. They're called colligative properties. The word actually comes from a Latin term that means bound together, which is perfect because all of these properties are tied together by that one single factor: the concentration of solute particles. And there are 4 main ones we're going to look at. Adding stuff to a solvent lowers its vapor pressure. That in turn makes its boiling point go up and its freezing point go down. And it also creates a fascinating force called osmotic pressure. So let's talk about boiling point. Why does adding salt to pasta water make it boil at a higher temperature? Well, you can think of the salt particles as tiny little roadblocks at the surface of the water. They literally get in the way, physically blocking some of the water molecules from escaping into the air as vapor. This lowers the vapor pressure, which means you have to pump in more energy, get it to a higher temperature to get the whole thing to boil. And pretty much the same logic works for freezing. To become ice, water molecules need to line up in a nice, neat, orderly crystal. But those solute particles get in the way again. They disrupt the party and make it harder for that crystal to form. To overcome all that chaos, the system has to get even colder. And that's why we salt the roads in winter. It's freezing point depression in action. Finally, you've got osmosis. You can think of osmosis as nature's obsession with balance. If you have two solutions separated by a special membrane, water will automatically flow from the less concentrated side to the more concentrated side, trying to even things out. This process is absolutely essential for life. It's how our cells manage their water, and it creates a very real, measurable force we call osmotic pressure. But just when you think you've got all the rules figured out, there's a plot twist. It turns out not all solutes play by the same rules, and some have a much more powerful effect than others. Okay, so here's the puzzle. If these colligative properties only depend on the number of particles, why is salt so much better at melting ice than sugar is, even if you add the exact same number of moles of each? What's going on there? The answer is all about what happens to them the moment they hit the water. To crack this puzzle, a brilliant chemist named Van 't Hoff came up with a little correction factor. He called it I. The Van 't Hoff factor is the missing piece of the puzzle, and it accounts for solutes that do something special. They break apart or dissociate when they dissolve. And here it is. This is the solution to our ice melting mystery. When you dissolve a sugar molecule, it just floats around as one particle. So for every 1 unit of sugar, you get 1 particle. Its I factor is 1. But when you dissolve table salt, NaCl, it breaks apart into 2 separate ions, a sodium ion and a chloride ion. So for every 1 unit of salt you add, you actually get 2 particles in the solution. Its I factor is 2. And what this means is we just need to make one tiny little tweak to our equations. For freezing point depression, for example, you just pop that little I, the Van 't Hoff factor, right in front. And that's it. That one change allows us to perfectly predict how these special solutes, which we call electrolytes, are going to behave. This chart just makes it crystal clear. Look at this. Compared to sugar, salt has double the ice melting power. And then you have something like calcium chloride, CaCl2, which breaks into 3 ions, 1 calcium and 2 chlorides. It has triple the effect. It's all about that particle count. So, really, the big takeaway here is that electrolytes punch way above their weight. They have this supercharged, magnified impact on solutions because they break apart and create more particles. And the Van 't Hoff factor, I, is the simple but brilliant tool that lets us measure and predict that impact. So, from what you cook in the kitchen, to how your own body works, to huge industrial processes, these fundamental rules of mixing are happening all around us, all the time. The next time you see salt being spread on an icy road, you'll know exactly what's happening at the molecular level. So, now that you know the rules, what everyday puzzle are you going to solve next?